Everyone, my name is Kejun Chen from the Department of Chemical and Biological Engineering, and today I'll be presenting my research called The Study of Gallium-Doped Polycrystalline Silicon Non-Oxide Passivated Contacts Through Non-Equilibrium Doping Method for High-Efficiency Crystalline Silicon Solar Cell. Starting with the big picture, solar energy is a sustainable and clean energy source, and from the left graph we can see that in Germany alone, solar energy increased drastically from 2002 up until now. And there are two types of solar cells, monocrystalline and multicrystalline. And if we look at the PV market of 2017, multicrystalline actually occupies the majority of this market due to its low price. However, the efficiency is also quite low compared to the monocrystalline solar cells, which will be the focus of this talk. Looking at the current monocrystalline solar cells, the workhorse cell is this aluminum back surface field, which is featured here with a p-type substrate and a diffused aluminum back. If we add dielectric layers and reduce the back contact area, we end up with the passivated emitter and rear cell, or PERC cell. We can also put the front contact to the back to have the interdigitated back contact cell, or IBC. However, these two cells still suffer from heavy recombination at the metal to bulk silicon interface, as metal introduces large density trap states and can cause severe recombination of these charge carriers. So to suppress this, we need to introduce some kind of passivating layers. One of the two methods is to add intrinsic and doped amorphous silicon, and this cell is the heterojunction with intrinsic thin layer HIT cell, which reached an efficiency above 25%. But this cell cannot withstand a high temperature process, mainly due to the lack of compatibility with the high temperature screen printing step. Another passivation technique starts with the bipolar transistor technology back in the 70s and was later introduced to the PV industry. Two inner layers were inserted between the metal and the bulk, a heavily doped polysilicon for charge separation, and a less than 2 nanometer thin tunneling oxide for passivation and also carrier transport. And this is the cell I'll be focusing on for my research. So this cell has been reported to reach an efficiency above 25%, but one of the bottlenecks of preventing it from reaching even higher efficiencies is the poor p-type contact as shown in these photoluminescent images. So the boron-doped polysilicon contacts appear darker, which means a low passivation quality. And the reason behind this is still debatable in the field, but can be generally attributed to the following three possibilities. The low diffusivity of boron in the oxide, which will cause boron pile-up issue, the peroxy linkage defects, and the Shockley-Rittal recombination. So the question is, how can we improve the p-type polysilicon contact? One way is to look for other p-type dopants for silicon that has certain properties we desire. In the group 3 category of the periodic table, the best candidate is gallium, since it has already been used in the bulk substrate to avoid light-induced degradation. A few advantages of gallium: it has a good diffusivity in the poly layer, and also a very high diffusivity in the oxide compared to boron. It also has a much higher segregation coefficient, which means it tends to diffuse right past the oxide and end up in the bulk. And indeed, this is what we see in the preliminary work. Here, from the secondary ion mass spectroscopy profile of gallium and boron, we see this peak at the oxide layer for boron, and no such pileup is observed for gallium. However, in order to use gallium in the highly doped polycrystalline silicon layer, we need to face the challenge of its low solid solubility, which is around 10 to the 19th inverse centimeter cube. Ideally, we want to achieve doping 1 order of magnitude higher than this to make good contact to the metal. So how can we dope silicon using gallium above its solid solubility limit? To start with, we need to use ion implantation to introduce dopants because we can precisely control the doping profile. Then use rapid thermal annealing, such as pulsed laser anneal, which can make a non-equilibrium condition possible. Some applications of this method including material used in superconductivity, thin film transistors, and also metal oxide semiconductor field effect transistor, or MOSFET. Now let's look at some math behind this. Depending on the laser energy densities, we can divide the behavior of the material after laser anneal into solid or liquid phase epitaxial regrowth. Taking liquid phase, for example, we can set up energy conservation equation assuming a unidirectional flow and an external heat source. And we can plot the temperature behavior of the material with respect to time. Here we see for a varying thermal conductivity with respect to temperature, we end up with a molten region which lasts about 35 nanoseconds after the initial pulse. This liquid phase will help the dopants to diffuse faster, and upon the removal of the laser, this will quickly freeze the dopants within the lattice, achieving this non-equilibrium doping. We can also control the maximum melt depth, that is how far this molten region goes, by varying the laser energy densities, and we see here, depending on the different ED, we'll have different profiles of the heat distributions. So for our preliminary experimental work, we collaborated with the University of Padova in Italy and uses excimer laser to rapidly melt and lock the dopants in place. The goal is to use this non-equilibrium methods to achieve to overcome the solid solubility limit. Simulations were performed to determine the desired laser energy densities, and we can see from this graph, energy density below 1100 millijoule per centimeter square is needed to not melt this tunneling oxide as shown here. From the preliminary results, we tested conventional dopants such as boron and phosphorus, and also the dopants of interest, which is gallium. By varying the energy densities, we are mainly looking at two criteria. One is the good carrier transport, and that is done by van der Pol-Hall measurements, which is shown on the right side. The other one is highly passivated contacts, which can be achieved through photoluminescence, or PL, which is shown on the left. The goal is to get a window where we see bright PL, which means good passivation, and also achieve the carrier concentration on the order of 10 to the 20th. We can see here that we've accomplished the first goal to some extent, but the second still requires some future work. We also need to examine the surface morphology of the samples to ensure the random pyramid features are not destroyed by too much heat. We see here as we decrease the energy density, there is less deformation of the pyramids. So it is important to balance all of the criteria that I just mentioned. Moving on to future works, we plan on examining planar or polished samples to gain a deeper understanding of the dopant profile using secondary ion mass spectroscopy, and also to use TEM to check the oxide uniformity as shown below in these images. So to conclude, here I demonstrated a new p-type dopant, gallium, to replace boron in a passivated contact solar cells through a non-equilibrium method using ion implantation and excimer laser anneal. The goal here is to overcome the low solid solubility limit of gallium in silicon and at the same time maintain good transport and passivation quality, ultimately increasing its power conversion efficiency. So with that, I'd like to thank all my colleagues at both CSM and NREL, and thank you all for your attention. Feel free to reach out to me if you have any question. Thanks.